Chapter 3, Section 3.1 talks about describing relationships, uh, namely relationships between two numerical variables. That's kind of the focus in this chapter. So first, let's start with some definitions. We've actually already covered these, so I don't want to spend a whole lot of time on them. A response variable is simply a variable that is the measure from the outcome of a study. And the explanatory variable is the variable that can help us explain or predict changes in the response variable. When we did chapter 4 and we're talking about experimentation, we're talking about explaining. Now we're going to kind of use those explanatory variables to make predictions about the response variable. So the response variable is what we're going to predict. That's kind of important. Example, height and weight, or weight and height. Tim wants to know if there's a relationship between height and weight. Kelly wants to know if she can predict a student's weight from her height. So she wants to use heights to predict weights. For each student, identify the explanatory and response variable. Are they interchangeable? Well, for Tim, it doesn't really matter. He just wants to know if there's a relationship. Makes a little more sense to say that height is the independent, is the explanatory, and your weight is a consequence of that height. But to be honest, you could say weight is your variable that you're measuring, and you're going to use it to predict height. It's interchangeable. So for Tim, they're interchangeable. They're interchangeable. However, because Kelly wants to use heights to make predictions on weights, she needs to make sure she sets this up a very specific way. So for her, heights are going to be the explanatory and weights are going to be the response, because that's what she wants to predict, the weights. So they're not interchangeable, no. How do we decide if there's a relation or an association between a categorical variable? First of all, these are interchangeable words in statistics. If we have two categorical variables, recall that we use two-way tables. We compare conditional distributions and determine if there's an association or not. Go watch a previous video if you don't remember that, but that's how we did it for two categorical. How do we decide if there's a relation or an association between two numerical variables? Well, that's what this chapter is about. Basically, the most useful graph for displaying the relationship between two quantitative variables is a scatter plot. So this is going to be our plot of choice for this unit. You guys know what a scatter plot is. Scatter plot is simply a graph of some numerical variable on the x-axis. In the previous example, Kelly would put the height on the x-axis, but it's numerical. And then the numerical variable weight on the other axis. And you just plot the point. Each point represents an individual whose height is that value and whose weight is that value. I'll let you read that comic if you want to. I guess AP Stats, the easiest way to lose points is to not label your axes. Title isn't even as important as the axes. If you just label these axes without any context, you can usually figure out what the graph is. So it's very important that you label the axes, okay? So let's do an example. The table below shows the data for 12 students in a stat class. Each member ran a 40-yard sprint and did a long jump, a running long jump. Make a scatter plot of the relationship. That's it. So I'm going to pause the video. So you guys, if you want to follow along, you put it in your calculator, but I'm just going to enter this into my TI Inspire. Where to enter it? Open up a new page, lists and spreadsheets. We're going to put sprint times here. And we're going to put jump distances here. But I am going to pause the video, so as to not waste your time. So if you want to put that in your calculator and follow along, go ahead and pause it and do it. So as you see, my data is entered into my calculator, and now we're going to make the scatter plot. On the TI Inspire, to make a scatter plot, we open up a new page. We want to open up a data and statistics page, option 5. And then we can use our mouse cursor if you want to, or I can just click down here. Basically, we click down on the x-axis. We want to add well, I guess we should talk about explanatory and response. Does it make more sense that sprint times would help us predict long jump times, or that long jump distances, or the other way around? Because you're running and jumping as far as you can, I would say the faster you run, the longer you could jump. So it makes sense kind of that this would maybe be the explanatory and this might be the response. But usually the question will talk about which prediction we're making. Well, they didn't ask us to do that. So let's just put sprint on the x. Sprint on the x-axis. So that's a univariate graph of sprint times, a dot plot. If we click this axis over here and add jump distances, we got our scatter plot. So in this section, we're going to talk about how to describe the relationship or identify if there even is a relationship. So I guess I would ask, does it look like there's a relationship? Well, it does kind of seem to be a trend that as your sprint times are higher, that means you'd be slower. If you're a slower runner, you don't seem to be jumping quite as far. Whereas if you're faster, if you have shorter sprint times, it looks like you're jumping a little bit further. So I'd say that is a relationship. If there was no relationship, then for people that have fast run times, you'd have some people that jumped far, some people that jumped medium, and some people that jumped a short distance. In the middle, you'd have long jumpers, middle jumpers, and short distance jumpers. And then for people that are really slow, you'd still have some very long jumpers, middle. So you'd kind of have random scatter all throughout. That's what no relationship would look like. So there's definitely a relationship here. Why do we study relationships between two variables? I can kind of think of two reasons. First of all, we want to know if they're related. We want to know if there's a relation. Which there's am I supposed to use? If there's a relation. And the second one would be if we want to make predictions, if we want to use sprint times to predict long jump distances. And again, in this section, we're going to kind of focus on those predictions. So how do we describe this relationship? Before, when we would describe univariate data, one variable data, we would cuss. We talk about the center, shape, spread, and unusual features. It's, kids like little naming things here, so we're going to do Duff's here. I guess think Homer Simpson's beer, Duff's beer, whatever. Direction, form, strength, and then unusual features. Unusual features is kind of the last one. You don't always have to say it, but if there's not any unusual features, you just do direction, form, and strength. So direction is the overall pattern. Are the points increasing or decreasing, or is there no pattern? If the points are increasing from left to right, we say there's a positive association. And if they're decreasing left to right, we say there's a negative association. If there's random scatter, we would say there's no association. So looking at this data set here, you can see that there's a negative slope, a negative relationship. Basically, as your sprint times increase, your jump distances decrease. That would be a negative relationship. Form. If we fit a curve to the overall pattern, what form would that curve have? The best fit curve is, if the best fit curve is a straight line, we would say the form is linear. This looks pretty linear to me. Basically, we kind of default to a linear relationship unless you see significant curvature. So there's a lot of spread, but I don't see any curvature, so I'm going to say it's linear. However, if the curve is not linear, then we can say it's nonlinear. Now, in the past, you've probably studied a lot of different models, sinusoidal, quadratic, all these things. In this class, we're just going to talk about linear and kind of nonlinear. Strength. The last one is to determine how closely the points follow that overall pattern, or how close they match the curve. Basically, if you had a relationship that was like this, where there's very little deviations from that best fit line, that would be a very, very strong relationship. If you have a lot of scatter about this line, best fit line, then it would be a weaker relationship. And then if there's no pattern, perfect scatter, we'd say there is no relationship. So I would probably say this is a moderately strong relationship. We'll talk a little bit later about how to quantify that, but for right now, moderately strong. We use phrases like no association, very weak, weak, moderately strong, strong, very strong. Unusual features. Are there any points that lie far outside the normal pattern of the other points? We can label these points outliers when describing the relationship. We're going to have to talk about outliers a little bit more later on, and we're going to learn about points that are influential as well. Example, describe the relationship between sprint time and long jump distance. So we're going to do our DUFs, direction, strength, spread, and unusual features. So I would say, oh, and then let's not forget context, 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 context. There is a moderately strong, that's subjective, but whatever, negative, linear, association, or relation, either word is fine here, between sprint time and jump distance. That's it. We got our strength, we got our direction, we got our form, and we have our all-important context. Positive association, negative association, you can read through that if you want. Basically, when an increase in your x's facilitate an average increase in your y's, as this increases, your y's increase, that's positive. As your x increases, if your y's tend to decrease, it's negative. And if your x increasing has no effect on your y values at all, you'd say there's no relationship. So let's describe a couple of these relationships. This shouldn't take too long. This is data for the US over the last 2 centuries. This is the year, and this is the population in millions. So as I can see, or as you can see, hopefully, that there's a very tight pattern, but it's not straight. So DUFs. There's no unusual features, so we're just DFS. There is a very strong, that's my strength, positive, there's my form, nonlinear, there's my, oh, I'm sorry, did I screw this up? Direct, oh, S, I'm sorry, positive was the direction, and then nonlinear was the form. I'm sorry about that. Relation between year and population in the US. Is there an association? Yes, there's an association. I just said it was very strong, positive, nonlinear. That's an association. Explain. Well, how can I explain the relationship? I guess I'd say as the year increases, the population also increases. You know, that's kind of at the core of what an association is. JCS shoe size. This is data from our school. We had recorded people's heights and their shoe size. Describe the relationship. I guess let's use some sentence here. There is a strength. A lot of variability here. Certainly relationship. I'm going to say moderately strong. It's going up. Positive. Looks like it's linear to me. Relation between height and shoe size. Is there an association? Yes, of course there is. How do you know? Because as your height increases, your shoe size tends to increase.